welcome to AI Advances. Today we're diving into a mind-bending experiment that pushes the boundaries of what we thought possible. Imagine a world where life springs forth not from primordial ooze, but from a sea of digital code. That's exactly what Google researchers have achieved in their groundbreaking simulation of life's origins. Stay tuned as we explore how they turned random data into self-replicating digital organisms, and what this could mean for the future of AI and synthetic biology. For decades, scientists have been captivated by a simple yet profound question: how did life begin? Traditionally, researchers have focused on recreating the conditions of early Earth in labs, mixing chemicals and zapping them with electricity. But Google's team took a radically different approach. They swapped test tubes for computer code, creating a digital playground where the building blocks of life could assemble themselves. This shift from wet labs to silicon chips isn't entirely new. Back in the 1950s, a scientist named Niels Ahl Baricelli was already tinkering with digital evolution. He created simple numerical entities that could change and reproduce over time. Fast forward to the 1990s, and we have Chris Adami developing Avita, a software platform where digital creatures compete and evolve. These pioneers laid the groundwork for Google's latest leap forward. So, how exactly did Google set up their digital petri dish? They chose a programming language called Brainfuck. Despite its colorful name, Brainfuck is known for its extreme simplicity. It has just a handful of commands, making it perfect for creating a chaotic, rule-free environment. Think of it as the digital equivalent of the primordial soup where life on Earth might have first emerged. Into this soup, the researchers tossed random snippets of code, their digital molecules. These bits of data were free to interact, execute, and even overwrite each other. There were no predefined rules, no guiding hand nudging them towards a particular outcome. It was digital chaos in its purest form. Now, you might be wondering, why go to all this trouble? What can we learn from digital life that we can't learn from studying actual living things? The beauty of this approach lies in its simplicity and control. In a test tube, countless chemical reactions happen simultaneously, making it hard to pinpoint exactly how life might have emerged. But in a digital world, researchers can track every interaction, rewind time, and run the experiment over and over with slight tweaks. As the digital molecules swirled and collated in their virtual petri dish, something remarkable happened. Out of the chaos, order began to emerge. Some of the random code snippets started to replicate themselves. These weren't just static copies. They were dynamic, self-reproducing entities. In other words, the most basic form of digital life had spontaneously appeared. This moment was nothing short of revolutionary. Without any guidance or pre-programmed instructions, the system had given birth to self-replicating programs. It's as if you threw a bunch of Lego bricks into a washing machine and they somehow assembled themselves into tiny robots that could build more of themselves. Ben Laurie, one of the study's co-authors, couldn't hide his excitement. He emphasized how these digital life forms arose purely from the inherent properties of the system. There was no hidden hand guiding their evolution, just the basic rules of the digital universe they inhabited. But let's pump the brakes for a moment. While this is undoubtedly a huge step forward, we're not talking about digital creatures with thoughts and feelings. These self-replicating programs are incredibly simple compared to even the most basic biological life forms. They're more like the first self-copying molecules that might have existed on Earth billions of years ago than anything we'd recognize as alive today. This brings us to an important point raised by Richard Watson from the University of Southampton. He cautions that while self-replication is a crucial first step, it's not the whole story of life. There's a vast gulf between a simple self-copying program and the intricate complexity of even a single-celled organism. Watson argues that other mechanisms are needed to bridge this gap and drive the evolution of more complex digital life forms. So, what does all this mean for the future of science and technology? The implications are truly staggering. Let's start with artificial intelligence. By understanding how complexity and self-replication can emerge from simple rules, we might be able to create AI systems that can learn, adapt, and even evolve on their own. Imagine AI assistants that could improve themselves over time, or robots that could repair and upgrade their own software. In the field of synthetic biology, this research opens up exciting new possibilities. Scientists might be able to design artificial organisms from the ground up, tailoring them for specific tasks. Picture bacteria engineered to clean up oil spills or produce life-saving medications. By understanding the fundamental principles of how life organizes itself, we could revolutionize fields like medicine, environmental science, and biotechnology. The experts are certainly taking notice. Susan Stepney, a professor at the University of York, called the experiment a great achievement. She emphasized how remarkable it is to evolve self-replicating programs from completely random starting points. This isn't just an incremental advance. It's a whole new way of thinking about the origins of life and the potential for creating artificial life forms. But as with any groundbreaking scientific advance, Google's digital genesis experiment raises some thorny ethical questions. As we get better at creating self-replicating digital entities, how do we ensure they remain under control? What are the potential risks of unleashing evolving AI systems into the digital wild? These are questions that ethicists, policymakers, and scientists will need to grapple with as the technology progresses. It's also worth noting that this research is still in its early stages. The digital life forms created in Google's experiment are a far cry from the complexity we see in biological organisms. Creating more sophisticated digital creatures will require immense computational power and more refined algorithms. It's a bit like the difference between the Wright brothers' first flight and landing on the moon. We've proven it's possible, but there's still a long way to go. One of the biggest challenges moving forward will be increasing the complexity of these digital organisms. While self-replication is an incredible start, it's just the first step on a long journey. Researchers will need to figure out how to encourage the evolution of more complex behaviors and structures within their digital ecosystems. This is where the raw power of modern computing comes into play. The current experiment pushed the limits of what a laptop can do, simulating billions of interactions per second. To take things to the next level, scientists might need to harness the power of massive supercomputers or distributed computing networks. The more processing power they can throw at the problem, the more likely they are to see the emergence of truly complex digital life forms. Another fascinating avenue for future research is the integration of machine learning and AI techniques into these simulations. By using AI to analyze the vast amounts of data generated by these experiments, researchers might be able to identify patterns and principles that human observers would miss. This could lead to breakthroughs in our understanding of how life organizes itself and evolves over time. The potential applications of this research extend far beyond the realm of pure science. In the field of robotics, for example, the principles of digital self-replication and evolution could lead to machines that can adapt to new environments on the fly. Imagine sending a rover to explore an alien planet and having it evolve new capabilities to deal with unexpected challenges. In the world of computer security, understanding how digital life forms emerge and spread could help us develop better defenses against computer viruses and malware. By studying the basic principles of digital replication and evolution, we might be able to create more robust and adaptive cybersecurity systems. Even in fields like economics and social science, the insights gained from these experiments could prove valuable. The way simple rules give rise to complex, self-organizing systems in the digital world might shed light on how economies function or how social movements spread. Of course, as we push further into this brave new world of digital life, we'll need to grapple with some profound philosophical questions. What exactly is the difference between a very complex computer program and a living organism? At what point does a self-replicating digital entity deserve moral consideration? These are the kinds of mind-bending debates that are sure to arise as the technology progresses. It's also worth considering the potential risks associated with creating self-replicating digital entities. While the current experiments are tightly controlled, as these systems become more complex, there's always the possibility of unintended consequences. Just as invasive species can wreak havoc on biological ecosystems, we'll need to be cautious about the potential impact of digital life forms on our increasingly interconnected digital world. This brings us to the crucial role of ethical guidelines and regulatory frameworks. As this technology advances, it will be essential for scientists, ethicists, and policymakers to work together to establish clear boundaries and safety protocols. We need to ensure that the development of digital life forms proceeds in a way that maximizes benefits while minimizing potential risks. Despite these challenges and ethical considerations, the potential benefits of this research are too significant to ignore. By understanding the fundamental principles of how life emerges and evolves, we might be able to tackle some of the most pressing challenges facing humanity. From developing new treatments for diseases to finding innovative solutions to environmental problems, the applications are limited only by our imagination. As we wrap up our exploration of Google's fascinating experiment, it's clear that we're standing on the brink of a new frontier in science and technology. The ability to simulate the origins of life in a digital environment opens up a world of possibilities that were once the realm of science fiction. But what do you think about all this? Could digital life forms one day rival their biological counterparts? What potential applications excite you the most? And what ethical concerns should we be considering as we move forward? We'd love to hear your thoughts in the comments below. This is a topic that's sure to spark some lively debate, and your insights could help shape the conversation around this groundbreaking research. If you found this dive into the world of digital life as fascinating as we did, don't forget to like and share this video. And if you want to stay up to date on the latest breakthroughs in AI and cutting-edge science, be sure to subscribe to our channel. We've got plenty more mind-bending topics coming your way. Thank you for joining us on this journey into the digital genesis of life. Until next time, keep questioning, keep exploring, and keep pushing the boundaries of what's possible. Who knows? The next big breakthrough in understanding life itself might just come from a world of ones and zeros.